And so which one's going to be a stronger acid? Well, we can tell by the carbons. These two carbons aren't the same. This is a +3, this is a -1. This carbon's electron rich, this carbon's electron poor. Electron poor carbon is going to suck the electron cloud away from oxygen, which in turn is going to suck the electron cloud away from hydrogen more significantly than here, because this oxygen is pulling electron density from carbon and hydrogen. So this one's going to be much more electron rich oxygen than this. This is going to be electron poor oxygen. And so that's going to make this one much less polar. In fact, ethanol we consider neutral, not acidic at all, because this hydrogen is not very positive. And so look at it. That's 10 to the minus 5 versus 10 to the minus 16. That's 11 orders of magnitude. So this is like a trillion times weaker of an acid than this. It still can be an acid, but it's a trillion times weaker. And so you'd have to have a very powerful base. Well, there are very powerful bases that will flush this proton off. And so we can get ethanol to react with an acid, as an acid. It just requires extremely strong base. Whereas acetic acid will react with most bases. All right. The other factor that we look at is the conjugate base, the stability of the conjugate base. And so that's factor number 3. I'm not going to write it down because I want to speed up. The stability of the conjugate base, number 3, is how localized is the negative charge. It turns out ethoxide is as powerful as hydroxide. And so this is one of the strong bases you didn't have to memorize because there's so many of them. And so ethoxide is a powerful base because just like hydroxide, the negative charge is localized on the oxygen. Whereas you might think acetate should be just as powerful as hydroxide because when you look at it, we got an O with a negative formal charge, but it isn't. Acetate is much weaker than hydroxide. The reason is because this charge is not localized. This charge is actually delocalized over 2 oxygens. And the charge is, Jay mentioned, is -1/2. Is that right? Or who mentioned? Was it you? Yeah, -1/2 on each. And so -1/2 charge means that this is going to be much more stable than this. And so this makes this a powerful base. The delocalization of that makes this a weak base. The more we can delocalize the negative charge, that is, the more resonance forms we can draw. So this is 2 resonance forms. If we could draw 3, 4, then the charge keeps decreasing. Like in carbonate, it's -1/3 because we can delocalize the negative. -2/3. In carbonate, it's -2/3 because we can delocalize the charge over 3 atoms. So the more atoms we can delocalize it, the weaker it becomes. So did I mention? Did I talk about Lake Oroville or something like that? Lake Oroville? Yeah. Did I mention that yesterday? Well, think about localized. If you localize all the water in Lake Oroville behind a dam, versus if you take all the water in Lake Oroville and delocalize it over the entire state of California, would it amount to much? No. And so Lake Oroville, all that water behind the dam is quite unstable. It's going to be quite reactive because this is why they're talking about evacuating. But if all that water were delocalized over the entire state of California, nobody would be evacuating. And so it's the same thing here. The more we can delocalize that negative charge, the more stable it's going to become and weaker it's going to be. And so we look at the stability of the conjugate base. The more stable the conjugate base, that is, the more stable the product, then the more reactive the acid. The less stable the conjugate base, the less stable the product, which means less reactive the acid. And so the more stable the conjugate base, this is what we remember, the more stable the conjugate base, the stronger the acid. Okay, chain length has little effect. Here, this is electron rich. This is already, what's the oxidation state on this carbon? This carbon is -2, 4, 6, 7. It's -3. That's electron rich. This carbon's electron rich. What's the oxidation state on this carbon? -2, 4. Well, no, actually, no, not -2, 4. 2, 4, 5, 6. It's -2. This is -2. This is -3. Which one? When we look at the strength, it turns out, this one is a little, this is acetic acid. Actually, we should do it. me just do this one here on the board. So which one would be a better acid? You know, what they're showing is the conjugate base. We'll look at the conjugate base also, but if we look at the acid itself, the acid is going to be this. And again, this Lewis structure doesn't have to be accurate. But when we look at the oxidation state on this, the oxidation state of this carbon is the same as the other one. The oxidation state on this carbon, however, is -3. And let's compare it to this. So we got a long chain here. The oxidation state on this carbon here is -2. So based on that, which one do you think should be a stronger acid? I would expect this one to be a stronger acid because this carbon's a little less electron rich than that one. The more electron rich this is, the more it can give electron density to this carbon, the less it takes away from this oxygen here, because this carbon is plus 3. Right, this carbon's +3. And so now if I have a -3 carbon bonded to a plus, so this is going to give more electron density than this one, a -2, right? But the situation here is I have a bunch of these carbons. This next carbon is also -2. And the next carbon after that is a -2. And finally, when we get to the last carbon is a -3. And so I got all of these electron rich. So this whole thing's electron rich. So do these, secondary, tertiary, these other carbons, that we call alpha beta carbons, do those impact this? And it turns out not so much because that's pretty localized. It turns out what's going to be the key here is the stability of the conjugate base, I think. And in terms of stability of the conjugate base, which one do you think is going to be slightly more stable as far as the conjugate bases go? As far as the conjugate bases go, you say they're the same, right? They're the same because we know that there's going to be resonance forms, and we know we're going to delocalize the negative charge over 2 oxygens. And so each of the oxygens is going to be -1/2. Each of these oxygens is going to be -1/2. They look the same, therefore we have to look deeper in the structure. Now this is going to be bonded to a -3. This is going to be bonded to a -2. So which one spreads out the water more? Which one delocalizes the negative charge more over the structure? Having a -3 here or -2 here? Well, I would predict having a -2 would help stabilize the negative charge over here more than having a -3 because it's more positive. But when we look at that, it doesn't make much of a difference. And so there are additional factors in this too. Because I would have predicted this acid to be a little bit stronger because of the less. But the one last factor is this, factor number 4. The one last factor is when we look at the stability, this has to be the stability in aqueous solution. Which one of these two is going to be more stable in aqueous solution? This one, which has a long hydrocarbon group, are hydrocarbons stable in water? That is, do they mix well with water? They're stable in the chemical sense, but they don't mix well with water. In fact, hydrocarbons and water don't mix. In other words, oil and water don't mix. And so the other factor we have to look at in addition to all these factors is how well this is stabilized in water, and this would be much more stabilized than this, because this we have to break apart a lot of water molecules. Water likes water, and to break apart a lot of water molecules to make room for this, which water doesn't like. And so you got to separate all these water molecules to make room for this. This is going to be less favorable. That being less favorable, this one is less stable in water than this one, and therefore it's weaker. But based on the charges, I would have expected this one to be stronger. Right? And so that's the fourth factor we look at. That fourth factor plays a role. The fourth factor is why lithium metal sits at the top of the redox chart. The reason why lithium metal sits at the top of the redox chart is because lithium ion is so stable in water. You know, because what's harder to ionize, lithium or potassium? Lithium is a heck of a lot harder to ionize than potassium. Potassium is a much bigger atom. Lithium is a much smaller atom. And so why is lithium king? Well, the reason why lithium is king is because of the stability of lithium ion AQ. This is very stable. Why is it stable? Because it's a small ion. The small ion can interact with the hydrogen, the oxygens in water. It helps stabilize it. Versus potassium ion is a big ion. And so the interaction is going to be a lot weaker. And so it's due to the stability of the hydrated ions. We call these hydrated ions. Well, this is going to be a lot easier to hydrate, that is, fit into the water than this. But still, they're comparable. 10 to the minus 5, 10 to the minus 5, they're pretty much the same. Well, let's take a look at these two. These two aren't the same. In fact, this chloroacetic acid is a stronger acid by 2 orders of magnitude, 10 to the minus 5 to 10 to the minus 3. 2 orders of magnitude would be 100 times stronger. So if we put a chlorine here, well, what did that do? Well, what's the oxidation state of this? The oxidation state of this is minus, well, this is 2, 4, 6, 7. It has 7 electrons. It's minus 3. The oxidation state of this, it has 2, 4, 5 electrons. It's minus 1. So this is a minus 1 versus a minus 3. Well, minus 3 is much more electron rich. A minus 1 is much less electron rich. And so this is the product, actually, the conjugate base. And so this conjugate base here is going to be much more stable than this, because we have less negative charge concentrated in there. And so since this is more stable, it's going to make it more acidic. On the other hand, we could have looked at it from the acid's point of view. From the acid's point of view, it would have led to bigger polarity. And so if we have a chlorine here, if we have a chlorine here that's minus 2, 4, actually, what is this? 2, 4, 5, 6, minus 2. Oxidation state versus a chlorine here that's, is that minus 2, 4, actually 0, 2, 4, 5, minus 1, sorry. If we have a chlorine here that's minus 1, versus a chlorine, a carbon here that's minus 1 versus a carbon here that's minus 3. Minus 3. This is a lot more electron rich. And so that's going to make this hydrogen a lot less polar than this. This is going to be a lot more polar. This is 100 times. That's chloroacetic acid. All right. I'll talk about bases in more detail later. So we'll just look at acids here. So if I went to dichloroacetic acid, what would happen there? If I had a dichloroacetic acid, what would its oxidation state changed to. So now it's going to be 2, 3. 2, 3, it's going to go to +1. Dichloroacetic acid, and is that going to make it more acidic or less acidic? It's going to make it more acidic. It's going to suck more electron density towards bicarbonate. If I want to trichloroacetic acid, if I go to trichloroacetic acid, then it goes to +3, making it quite a bit more acidic. And so trichloroacetic acid is considered a strong acid, or borderline strong. So this is pretty much a strong acid. All right, I'm going to stop talking here. We still have a lot more to cover with the amines and other bases, and then some more acids. A little bit about Lewis acid base. That's it. This is a preview. So why don't you continue working on the structures there, and I'll come around and take a look at it.